All right, welcome to the second half, or the second video lecture for topic 12, factors that affect Bronsted-Lowry acid-base strength. Now, all of the information that I'm going to be presenting in this video lecture is right in your textbook in Sorrel. So, if you prefer to get that information from Sorrel, you can go ahead and get it there. However, if you prefer to get the content from the video lectures, I'm going to go through everything that Sorrel talks about in terms of acid and base strength. So, let's begin with acids, since we live in a pKa world and we like thinking about things in terms of acids and conjugate acids as opposed to thinking about things in terms of bases. I'm going to start off this just talking about, the different factors or physical or molecular properties that influence the strength of acids, right? And so so the first thing that we're going to look at, right, I'm going to call size, right? So number one, first factor is going to be size. So here specifically, I'm talking about the size of the conjugate base, right? And these are for our halohydric acids, right? So these are our HCl's, our HBr's, our HF's, and our HI's. And so if we list these out along with their pKa's, so we'll go HF, HCl, HBr, and HI, and we're going to go ahead and put down their pKa's. Now again, you don't need to memorize specific pKa's. I'm going to be using very specific values for all of the acids that I talk about in part 2 in this video lecture. And again, if you want to know them, that's great. I'm going to expect you to know the ballpark values that were presented on the sheet that was handed out in class, right? So if we list out the pKa's for these acids, right, HF has a pKa of about 3.3, HCl is pKa of -7, right? HBr is a pKa of -9, and HI is a pKa of -10, right? So these are the pKa's of the acids. Now, if we take a look at the conjugate bases of these acids, right, we would have F-, Cl-, Br-, and I-. Now, when I talk here about size, I'm talking about the atomic radius of these conjugate bases. And the atomic radius increases as we move from fluorine to iodine, essentially as we move down that column or down that period on the periodic table, right? So iodine is the largest, fluorine is the smallest. Now, the consequence of this difference in size is that each of these has a single negative charge, right? 1- on each of these ions, and so the size or volume of that ion is going to determine how diffuse or how concentrated or diffuse, right, that charge is. So for a very small ion like fluorine, we can say that negative charge, right, that negative charge is concentrated. And for iodine, very large atom, we can say that negative charge is very diffuse, right? It's spread out over a larger volume. What this means is that this is a strong negative charge. It's going to be very good at forming new bonds, right? Which means it's going to be a strong base. This fluorine ion is going to want to use that negative charge, that concentrated negative charge, to grab onto a proton, okay? And so that's going to make this a strong base. Similarly, right, but conversely, because this negative charge on this iodine is so spread out over a large volume, right, it's not very concentrated, it has a lot of room to exist, and it's relatively comfortable around that, and it's that negative charge isn't particularly interested in forming a new bond to a hydrogen atom, and so this I minus is going to be a weak base. And so now we can, because we know that I minus is a weak base, it makes sense that HI is a strong acid. And similarly, because we know F minus is going to be a strong base, it makes sense that, relatively speaking, in this comparison, HF would be a weaker acid. And that is reflected, again, in their pKa's. Right? The next factor that's going to affect things is electronegativity. So for electronegativity, the second factor that we're going to consider we are concerned with the electronegativity of the atom that is going to be holding on to, or the atom that is bonded to, that acidic proton. And so we're going to take a look at 4 different potential acids, right? Let's take a look at methane. We're going to take a look at ammonia. We'll take a look at water. And then finally, we're going to take a look once more at HF. And so now we are interested in the electronegativity of the atom that's directly bonded to our acidic hydrogen. So for methane, that's going to be carbon, right? For ammonia, that's going to be nitrogen. For water, that's oxygen. And for HF, that's going to be fluorine. Now, I'm going to go ahead and list out the pKa's for these 4 different potential acids, right? So for methane, the pKa of this hydrogen is going to be 48. For ammonia, the pKa of that hydrogen is 38. For water, the pKa of that hydrogen, right? And again, I'm using specific values. You're only expected to know the ballpark values on the sheet that I distributed, right? But for water, that pKa is going to be 15.7. And as we saw for our first factor, right, the pKa of the hydrogen in HF is approximately 3.3. So we can correlate this trend, right, of decreasing pKa, right? It is inversely proportional to, or it has an inverse relationship with, the electronegativity of each of these different atoms that are bonded to the acidic hydrogen, right? So now for the electronegativity, I'm going to abbreviate that En here, right? For carbon, the electronegativity of carbon is 2.5. The electronegativity of nitrogen is going to be 3.0. I'm using electronegativities from the Pauling scale. There is another scale for electronegativities, but I stick with the Pauling scale, which is more widely adopted, right? For oxygen, that electronegativity is going to be 3.5. And finally, for fluorine, right, that electronegativity is 4.0. So we see as how the electronegativity increases, the pKa decreases, right? Or said another way, as the electronegativity increases, right, that acidity also increases, okay? So when we have a very electronegative atom, right, that's going to give us a lower pKa, stronger acid. If we have a low electronegativity, that's going to give us a higher pKa, a weaker acid. And so now we can make these qualitative comparisons, right, using electronegativity as a factor to determine this, right? And so there's one more thing that I'm not really talking about here that I'm going to mention very briefly, right? Why is it that having a higher electronegativity gives us a stronger acid? Well, if we think about, or excuse me, I haven't mentioned it yet and I'm going to now. If we think about the nature of those conjugate bases, right? So here we have H3C, there's our lone pair. We'll have H2N, Here now we have two lone pairs, OH minus or F minus. We can think about how does the electronegativity of that atom, right, carbon, nitrogen, oxygen, or fluorine, affect that new lone pair on our conjugate base? Well, in the case of carbon, electronegativity 2.5, that number tells us that the carbon atom isn't, really strongly holding on to, right, this new lone pair, right? It's got a low electronegativity. It's willing to let that lone pair be a little bit further from it, and thus that lone pair is more readily able to grab onto a new hydrogen, which means that it's more favorable for this lone pair to form a new bond. Whereas here in fluorine, with an electronegativity of 4.0, that new lone pair that is on our conjugate base, that's held very tightly to the fluorine. The fluorine nucleus does not easily want to give up that new lone pair that it got because it's so electronegative. And so now that new lone pair on fluorine, it's very close to the nucleus, and it's not really able to go, it's not as free to go and form a new bond to regenerate the acid. And so we can now give a qualitative assessment for these four conjugate bases and say that here now, because this lone pair on carbon, a little bit further away, more able to go and grab a hydrogen atom, right? This is going to make it a stronger base, which makes our F minus a weaker base. And if we remember back to our general rules for strong acid, weak conjugate base, weak acid, strong conjugate base, we can apply the converse of that, where a stronger base will result in a weaker acid. So this is going to have form a weaker acid, which fits with the pKa that we see for methane. Similarly here, our weak base will form a stronger acid, which fits with our pKa for HF, right? And so now we can use electronegativity to be able to qualitatively rank the strengths of different acids. Okay, the next factor we're going to take a look at is going to be hybridization of the atom that's bonded to the acidic proton. So for hybridization, right, factor 3, we can only really make this comparison among similar types of atoms. So what I'm going to do is I'm going to put three different carbon acids, so to speak, with different hybridizations. Once again, here we're going to start with methanol. We're going to take a look at an alkene as well. And then finally, we're going to take a look at an alkyne. And now, listing out the pKa of these acidic hydrogens, for methane, that hydrogen has a pKa of about 48. Off of our alkene, that hydrogen has a pKa of about 44. And finally, for our alkyne, that hydrogen has a pKa of about 25. Now, what causes the difference between these is the hybridization of the carbon atom that acidic proton is bonded to. And so let's list that out right now. So here, this carbon in methane is sp3 hybridized. Our carbon in ethylene, right, is going to be sp2 hybridized. And finally, our carbon in acetylene is sp hybridized. So how does this play a role? Well, let's think about what the nature of the orbital on carbon that's making the bond to that hydrogen is. So here in methane, that orbital, that sp3 orbital, has 1/4 s character and 3/4 p character. Here in our alkene scenario, we have 1/3 S character and 2/3 P character. And then finally in our alkyne scenario, we have 1/2 S character and 1/2 P orbital character. Now, recall back from our discussion about atomic orbitals that an s orbital is always going to be smaller than a p orbital. And a hybrid orbital is going to behave in a fashion that is related to how much s character it has and how much p character it has. And so we can make these size comparisons between our three hybrid orbitals, right? We know that p orbital is the largest. We know that an s orbital is the smallest. And so now moving from largest to smallest and putting in our hybrid orbitals, the hybrid orbitals that has the most p orbital character to it is going to be the largest hybrid orbital. So that would be our sp3 orbital. From there, our sp2 orbital is the next smallest. Whoops. sp2. And then finally, right, the smallest hybrid orbital is going to be the sp orbital, which is going to be larger than just an atomic s orbital. Right? So this means that when we generate the conjugate bases, right, so here now we're going to have H3C minus with a lone pair. We're going to have, I'm not drawing the other half of that alkene, CH with a minus on an sp2. And then finally, we're going to have, right, just drawing the deprotonated side of our alkyne, triple bond C with a minus charge and a lone pair, right? From our sp3 example, sp2 example, sp example. Now, since our sp3 orbital is very large, right, in comparison to an sp orbital, right, sp3 is going to be bigger, right, that means that the electrons are further away from this basic carbon, right, this carbon that is now a base, which means that they are able to more easily able to reach out and grab a proton and form a new carbon-hydrogen bond. That ease of ability to grab that hydrogen and to make that bond makes this a stronger base. If we look at our sp example, because that sp orbital is small, it's holding those electrons closer to the carbon nucleus in our alkyne, in our deprotonated alkyne, right? They're a lot closer, and so it's not, these electrons here in our deprotonated alkyne aren't as free to reach out and make a new bond to a hydrogen atom. That's going to make this a weaker base. And we can use our rules from the first video lecture for topic 12, which tells us that means that here, methane, which generates a strong conjugate base, or a stronger conjugate base, I should say, will be our weaker acid, which is verified by its pKa. And acetylene, which forms a weak conjugate base, is going to form a stronger acid, which is once again verified by its pKa. And so now this is how hybridization influences the strengths of different acids. And you can apply this similarly to nitrogen-based acids or oxygen-based acids, right? Anytime we're going to have hybridization changes, we're going to be able to see this same type of a pattern. All right, so the next factor we need to look at is electron delocalization. So our fourth factor, electron delocalization. Right? For this, I'm going to use two oxygen acids for our examples. So the first oxygen acid I'm going to use is going to be acetic acid. And the counterexample for this is going to be an alcohol, and I'm going to use ethanol. Now, when we generate the conjugate bases of these for acetic acid, and ethoxide, we see that for our acetate anion, our deprotonated acetic acid, we can draw a resonance structure for it. We can delocalize that negative charge across a few different atoms. So our resonance structure, or our second resonance structure for it, would look like this. And our overall resonance hybrid looks like this. And we have a partial negative on each of our oxygens. We have distributed that negative charge. It is now involved in resonance. However, for our conjugate base of ethanol, ethoxide, we can't form any resonance charges, right? Or, sorry, resonance structures. We can't delocalize the charge that is formed on this oxygen atom. So here now we have delocalized charge. And here we have a localized charge. The consequence of delocalizing this charge, right, means that this electron pair, right, that we can move around in resonance is zipping back and forth, back and forth, back and forth all around between these three atoms, right, to give us this delocalized, right, resonance hybrid. That means that that pair of electrons, the ones that form that negative charge, aren't as available to go and form a new bond to a hydrogen atom and regenerate our acid, right? They are less available because they're too busy being delocalized across, right, our deprotonated functional group. And so that's going to make our conjugate base of acetic acid a weak base. Whereas because in our ethoxide, our conjugate base of ethanol, right, because that lone pair is localized, it's trapped on that oxygen atom, it has nowhere else to go, all it's waiting to do is to find some hydrogen atom to form a new bond, right? And so this localized charge makes this species, ethoxide, a strong base. Which means that acetic acid should be, because its conjugate base is weak, acetic acid should be a strong acid. And because its conjugate base is a strong base, ethanol should be a weak acid. And this is confirmed by the pKa's of these two different molecules. So again, we know from our chart that the carboxylic acid pKa is approximately 5, right? And that our alcohol pKa, for our purposes, is approximately 18, right? This tells, and this is, right, fits with what we've just seen here. Acetic acid is a stronger acid, right? Ethanol is a weaker acid. So the last factor that influenced the strength or weakness of acids is going to be what's called inductive effects. And we're going to take a look at that just here in a moment. So for inductive effects, right, our fifth factor right, this is all about the presence of electronegative atoms, right, within the overall structure of the acid, right? And the proximity of that electronegative atom to our acidic hydrogen, right? And this is best demonstrated by taking a look at some derivatives of acetic acid that are now substituted with electronegative atoms. So we'll take our parent acid, and I'm only going to draw one of the methyl hydrogens for acetic acid, because I'm going to start trading that out for more electronegative atoms, right? And again, I'm going to use specific values here. You just need to know how this effect, right, impacts the strength of acids. I'm not going to expect you to know specific values for the different acids that I'm going to show right now, right? But the exact pKa of acetic acid in water is 4.75. If I take that hydrogen atom off the methyl group and I replace it with something a little more electronegative, right? So electronegativity of hydrogen is 2.1. If I replace it with something a little bit more electronegative, let's say an iodine, right? Iodine's electronegativity on the Pauling scale is 2.5, so a little bit more electronegative than hydrogen. We see that that changes, that lowers the pKa of our acidic hydrogen to now from being at 4.75 to having a pKa of 3.12. And the reason this occurs is because we can think of each of these 4 bonds between the iodine and the hydrogen as a dipole, right? And so we can see our carbon-iodine bond is polarized this way. That induces a polarization between these 2 carbons in that direction, which induces an increase in the polarization between the carbon and the oxygen this way, which induces and increases the polarization in the oxygen-hydrogen bond this way. And so by increasing the electronegativity over here, I have this chain effect of pulling electron density away from this hydrogen atom, making this oxygen-hydrogen bond weaker, and thereby making it easier for my acid to let go of its proton, right? I'm now increasing the Ka of this dissociation, right? I'm increasing the propensity for the acid to dissociate, which means I'm going to overall lower my pKa. And as we increase the electronegativity of this new group we've put on, right, we'll see that that trend continues. So if I move to something that's a little bit more electronegative, now bromine, with an electronegativity of about 2.8, that in turn takes my pKa from 3.12 down to 2.9. Yep, 2.9. If I then move even a step further and I change that bromine to a chlorine, chlorine having a electronegativity of about 3.0, right? That's going to take my pKa here down to 2.85. And then finally, if I go to something very electronegative like fluorine, which has an electronegativity of 4, that drops my pKa down to 2.59. Right? So in all of these examples, the atom that I'm switching out, or the location of increasing electronegativity, is 1, 2, 3, 4 bonds away. Right? And so we can see how this trend now drops us from approximately 5 to about 2.6 as we increase electronegativity, moving up a period on the periodic table, right? As we go from iodine to bromine to fluorine to chlorine. Now, it's not only the type of atom that can affect this process, but it's also the number of those electronegative atoms that can affect this process. So, I'm going to take a pause and we're going to take a look at this quantity effect next. So, we're going to use 3 examples to see how the quantity of electronegative atoms affects pKa of an acid. So we're going to go back to our chlorinated acetic acid. And now I'm going to add one more chlorine atom to that carbon. So here I'm now going to have 2 chlorines and a hydrogen. And then I'm also going to take a look and replace all of those hydrogens with chlorine atoms and see what the effect is when I do that substitution. So, if you recall from what we were just looking at a moment ago, the pKa here, if I have 1 chlorine atom 4 bonds away from my acidic hydrogen, my pKa is about 2.85. But now when I add that second chlorine atom, now I have two groups that are 4 bonds away, pulling electron density out of this oxygen-hydrogen bond. So, right, I've made this bond now even weaker. This hydrogen should be able to fall off even easier, right? I've increased this propensity for dissociation. And we find that the pKa in our dichloroacetic acid fits that expectation, right? Its pKa is about 1.48. Finally, if I remove that last hydrogen, replace it with a chlorine, now I have 3 electronegative atoms, or more electronegative atoms, that are all 4 bonds away. I should weaken this oxygen-hydrogen bond even further, and that's verified by the pKa. So for trichloroacetic acid, our pKa drops all the way down to 0.7, making this an incredibly strong acid. So one of the issues is what type of electronegative atom we're putting in there, or how electronegative is that new atom. That's, as we increase electronegativity, it's going to reduce density in the oxygen-hydrogen bond. And how many of those electronegative atoms I put, right? As I increase the number of electronegative atoms, I further weaken that oxygen-hydrogen bond and further drop my pKa, making a stronger acid. The last thing we need to take a look at in terms of inductive effects is how far away, right? So everything we've done so far has only been an electronegative atom 4 bonds away from our hydrogen. What if we start moving further and further out in a molecule? And so we're going to take a look at how that impacts it next. So in terms of distance from our acidic hydrogen, this example, or this scenario, is best demonstrated by looking at chlorinated derivatives of butyric acid, right? So butyric acid, here's 1, 2, 3, 4 carbons, right? And I'm now going to draw 3 different derivatives of this. And I'm going to put the chlorine at a different carbon atom in each of these 3 derivatives. So here we have 2-chloroacetic acid versus 3-chloroacetic acid versus 4-butyric acid for all of these. 2-chlorobutyric acid, 3-chlorobutyric acid, 4-chlorobutyric acid. So here, in our 2-chlorobutyric acid, there are 1, 2, 3, 4 bonds between our electronegative atom and our hydrogen, and we have a pKa of approximately 2.86. When I move to 3-chlorobutyric acid, right, so here I was 4 bonds away. When I move to 4-chlorobutyric acid, I have 1, 2, 3, 4, 5 bonds between my electronegative group and my acidic hydrogen. And what we find is, because we've moved that electronegative group 1 more bond away, its overall effect on the strength of our oxygen-hydrogen bond decreases, right? It's further away. This inductive effect isn't as strong as it moves away from that oxygen-hydrogen bond. And we'll see that in this scenario, our pKa is now 4.05. And then finally, in 4-chlorobutyric acid, where we are now 1, 2, 3, 4, 5, 6 bonds away, right? What we see is now we are very far away, right? The effect of this chlorine atom on the oxygen-hydrogen bond is going to be much weaker. And we're going to see that here, right? This hydrogen now has a pKa of approximately 4.52. So to recap, when considering inductive effects, you need to consider not only the type of electronegative atom and the strength of its electronegativity and how that impacts the bond, but you also need to consider the quantity of electronegative atoms and how that's going to impact the strength or weakness of that acidic hydrogen bond. And then finally, you need to you need to consider the location or the distance of that electronegative atom from the acidic bond as well. Right, so all three of those factors fall under inductive effects, and if you recall, we had 5 total things that we needed to consider. Size, sorry, I need to refresh myself as well. So size was the first one, electronegativity was the second one, right, and that's electronegativity of the atom directly bonded to the acidic hydrogen. Hybridization was the third, right, of the atom directly bonded to the acidic hydrogen, and then fourth was electron delocalization. Can we spread that newly formed negative charge in our conjugate base? Can we spread it out? And then 5 was our inductive effects. Right? I'm going to move on now to take a look at what are some of the factors that influence the strength and weakness of a base. So when considering factors that impact the strength or weakness of our bases, right, our 2 major bases that we're going to be working with this semester are going to be nitrogen bases and oxygen bases. And so in our discussion about the strength of acids earlier in this video, we talked about delocalization, and we specifically looked at how that impacts oxygen bases, right? We looked at acetate ion, anion, and we also looked at an alcohol anion, or an alkoxide as they're known, right? So I'm not going to get into oxygen bases for the purposes of this of our video today. I'm going to focus what I have to finish up with on our nitrogen bases, right? So the parent compound of all of our nitrogen bases is ammonia. Ammonia is both a Lewis base. It can donate an electron pair. It is also a Bronsted-Lowry base. It can accept another hydrogen, right? So it is a base in all the ways that we think about it, right? So since we don't use pKa's in organic since we don't use pKb's in organic chemistry, we have to think about everything in terms of pKa. And so we have to think about all of our bases in terms of their conjugate acids, right? And they're more in their protonated form. And recall that a weak conjugate acid implies a strong base, and a strong conjugate acid implies a weak base, right? So the pKa of ammonia's conjugate acid, so here's ammonia's conjugate acid, right? The pKa of any one of these hydrogens is going to be approximately 9. And that value is what's taken directly from the chart that I handed out in class. So this is a relatively weak acid at a pKa of 9, which means that ammonia should be a relatively strong base. And we find that to be generally true. But this is just the parent of all amines. What happens when we start replacing these hydrogens on ammonia with alkyl groups? Well, alkyl groups are electron donating, and we're going to see this, how alkyl groups are electron donating. We're going to get into the specifics of that when we get to, I believe it's topic 14, SN1 reactions, but that's going to be later on in the week. So for now, I'd like you to just take it on trust when I tell you that alkyl groups are electron donating. And so if we're donating electron density into this nitrogen, right, that should then make this lone pair more able to go out, right? It's a little bit freer to go and grab a hydrogen. And we do find that that's true. So if we look at a few different nitrogen bases, and I'm going to start with ammonia, if I replace one of those hydrogens with an alkyl group, I'm just going to pick methyl to be the alkyl group that I substitute on there. I can generate methyl, I make methylamine. And if I replace two of those hydrogens, right, I'm going to make dimethylamine. Now, I'm going to stop for just a moment at dimethylamine because the situation changes a little bit, right, when we get to a nitrogen with 3 alkyl groups on it. Before I move further, I want to introduce a new way to describe these molecules, right? A nitrogen that has 2 hydrogens and 1 alkyl group is known as a primary amine. A nitrogen that has 2 alkyl groups and 1 hydrogen is known as a secondary amine. And what we're going to find is that as we move from ammonia to our primary amine to our secondary amine, their conjugate acids, so H4N plus versus H3C NH3 plus versus H3C, we're now going to have 2 of these on our nitrogens, on our nitrogen NH2 plus, right? The pKa of these conjugate acids begins to increase as we move from ammonium to methylammonium to dimethylammonium, right? And so since our pKa's are increasing, and these are approximately 9, 10, and 11, again, those are approximate values, right? That means this is a stronger acid. Our dimethylammonium would be the weaker acid. And so now, looking back at our amine bases where we started, that means that dimethylamine is going to be the stronger base, and ammonia is going to be a weaker base. Now, the reason the situation gets a little bit more complex when we talk about tertiary amines is because even though that third alkyl group is going to increase electron density on the nitrogen and will make it a little easier for that nitrogen lone pair to go out and grab a hydrogen, form a hydrogen, nitrogen-hydrogen bond, by adding in that third alkyl group, we have also increased steric bulk around that nitrogen. Right? And so by increasing the steric bulk around that nitrogen, it's more difficult for a hydrogen to approach close enough to go ahead and form that bond with our nitrogen using the nitrogen's lone pair. And so unfortunately, for tertiary amines, the steric bulk tends to outweigh the electron donating effects of the 3 alkyl groups. And what we find is that if we take a look at it, this trimethylamines conjugate acid, so here now in between these two, I'm going to put CH3,3NH plus, which is our protonated form of trimethylamine. Its pKa falls somewhere between ammonia and our primary amine, right? So again, now here, when I have 3 alkyl groups on a nitrogen, this is known as a tertiary amine. And the conjugate acid of our tertiary amine base is going to have a pKa of approximately 9.5, right? For all alkylated amines, I'm going to expect you to know the pKa of the conjugate acid is ballpark 10, the value that's listed on the sheet. You should know that ammonium is about 9, right? I'm not going to expect you to know these specific differences. We can just ballpark them all at about 10, pKa of 10 for the conjugate acids. And so, right, now we have ammonia is going to be our weakest base. Our tertiary amines are going to be a little stronger. Our primary amines are going to be a little bit stronger than that. And finally, our secondary amines are going to be really, really our strongest out of this series, right? So we've taken a look at the effect of adding alkyl groups to our nitrogen. The next thing we need to do is take a look at the effect of the hybridization of the nitrogen, similar to how we took a look at hybridization for acids. So when considering hybridization for nitrogen bases, I'm going to just use 2 molecules, right, for our examples. One of these we've seen before, our dimethylamine, which is a secondary alkylamine. And the other one is going to be pyridine. right? And so these are both bases that are frequently used in organic synthesis, right? The difference here is that we have a sp3 hybridized nitrogen for dimethylamine versus an sp2 hybridized nitrogen in pyridine. Now, the pKa of the conjugate acid for both of these, so I'm going to put pKa, and now this is for the conjugate acid, right? pKa for the conjugate acid of dimethylamine, again, we're just going to use the value off the chart. That's going to ballpark at about 10. Whereas the pKa for the conjugate acid of pyridine is going to be about 5. So that tells us that since the conjugate acid of pyridine is a stronger acid, that means that pyridine should be a weaker base. And here we have a weaker acid relative. We also would have a stronger base. Now, if you think back to when we were looking at our carbon-based hybridization examples, right? For sp3, we had the conjugate base of methanol, or excuse me, of methane, and we had the conjugate base of an alkene. And we said that since that sp3 orbital, we're going to talk about our carbon now, since that sp3 orbital was relatively large because of the amount of p orbital character it had, those electrons were far away enough that they were very ready to go out and reach out and make a new bond to hydrogen. And the same thing here is true. That sp3 orbital is pretty big. So those two electrons don't have to stay right next to that nitrogen, right? And for dimethylamine, they can go all the way out here. They have a lot more space and room to reach out and make a bond to a proton. Where in our sp2 orbital is smaller than our sp3 orbital. And we see now that similar to our deprotonated alkene, the electrons on that sp2 hybridized nitrogen can't reach out quite as far, and so they are not as available to go ahead and make a bond to a new hydrogen, right? So again, as we change our hybridization, right, moving from a larger hybrid orbital to a smaller hybrid orbital, right, our electrons become less available to make a bond, which means that a large hybrid orbital gives us a strong base, and a small hybrid orbital gives us a weaker base. All right. That takes us to the last thing that we need to look at in terms of talking about the strength and weaknesses of bases, and that's going to be, once again, electron delocalization. So for electron delocalization in nitrogen bases, right, a great starting compound for us to consider this topic, right, to consider in this topic is going to be aniline. So here now, as a refresher, is the structure of aniline. And keeping in mind that we live in a pKa world, right, we judge this not based on, we judge the strength of this base not on pKb's, but on the pKa of the conjugate acid. So the pKa of the conjugate acid here is approximately 5. Right? About the same as a pyridine. Now the reason for this, right, that we have a strong conjugate acid implying a weak conjugate base or a weak base is because this electron pair can actually delocalize into this aromatic ring, right? And so we can distribute this lone pair around the ring, right? That delocalizes the charge, which makes that electron pair less available to form a bond to a hydrogen atom, right? To get protonated at that base, at that basic site. So now here, delocalization right, makes this a weaker base. Now, we can affect the pKa of our anilines by adding either electron donating or electron withdrawing substituents somewhere onto this aromatic ring, right? And so I'm going to give two examples here. We're going to take an aniline derivative and we're going to put a methoxy group off of the ring. We're going to take another aniline derivative. Whoops. And this time, however, we're going to put a electron withdrawing group off of the ring. Right? So nitro groups are electron withdrawing, right? An indicator of that is the positive charge, right? The positive formal charge on that nitrogen. Let me clean this up just a little bit for you. Right? And a oxygen, right, an sp3 hybridized oxygen is electron donating, right? So whenever we see this, we're going to think electron donating. Whenever we see nitros, we want to think electron withdrawing. So let's think about what that does. Well, since this oxygen group or this methoxy group is electron donating group, we can think of it, and it's true, that one of the lone pairs on the oxygen can donate into the ring, right, all the way towards this nitrogen and increase electron density on this nitrogen, right? So this electron donating group increases electron density at the aniline nitrogen. Whereas if we think about this nitro group, right, this nitro nitrogen wants to get, like, it's electron deficient, right? It's got a positive charge. It wants to bring electrons towards it. And so we can think that it's pulling, right, electrons out of the ring, which is going to have this effect through resonance that's going to pull electron density out of that aniline nitrogen. So now here our electron withdrawing group decreases electron density at the aniline nitrogen. Right? So what does this mean? So because here we're increasing electron density on the aniline nitrogen for our methoxy electron donating group situation, that means that this lone pair on the nitrogen is more available to go and form a bond, right, to a new hydrogen atom. It's more available to serve as a base. So that's going to make this a stronger base, right? And that means that its conjugate acid is going to be a weaker acid. So relative to aniline, it's going to have a higher conjugate acid pKa. For the situation where we have our electron withdrawing nitro group, right, again, this is going to decrease electron density on this aniline nitrogen, which means that this aniline nitrogen, this lone pair here, is less available to go out and make a bond to a hydrogen, right? That's going to make this a weaker base. Which means that it's going to have a lower conjugate acid pKa, right? So now we can take a look at how electron delocalization affects the strength or weakness of a base. Now, I've used throughout this video a lot of very specific pKa values, right? I will not be expecting you to do that. What I do expect you to do, or what I will expect of you, is that you are able to compare 3 acids and rank them in terms of relative strength, or rank them from strongest to weakest. I'm going to also expect you to be able to take 3 bases and rank them from strongest to weakest in terms of how strong of a base or weak of a base they are, right? So again, all of this information I've presented to you in this video is also directly from your Sorrel reading, just one more format. For those of you who may prefer video lectures over reading, some of you may prefer reading over video lectures, and that's perfectly fine as well. So once again, thank you for watching. If you have any questions, please bring them to conference, lecture, office hours, or feel free to make an appointment with me and we can talk about the material. Have a great day.